for any length of time, any at all. That's up to the decision of the financial institution to decide how often they want to compound. They can even compound multiple times per second, milliseconds, like 1,000,000 times a second it can be compounded, or more. So in order to calculate that, we have to learn some basic calculus function type information, and that's a limit. A limit is a function that occurs in calculus. So what a limit does is it assigns a number value to a value that's unreachable. Okay, so just, I'm going to come back to this for a second, but let's just say I have a half and I square it. That gives me a fourth. And let's say I square that. I get a 16th. And I square that. And I'm going to get a 256th. And I keep going, and I keep squaring and squaring and squaring and squaring and squaring. This denominator is just going to keep getting bigger and bigger and bigger and bigger and bigger. But it will never go to a certain, as long as I keep squaring forever, it'll keep, the denominator will keep getting bigger forever. It'll never reach a certain set number. But the graph for that looks like this. And it gets closer and closer and closer and closer to 0. But it never touches 0. Because we could have, 1 over a billion. Still not 0. I can have 1 over a Google. Still not 0. It's so close to 0, but it's still never going to quite be 0. And the limit takes care of that and says, okay, we'll just call it 0. And that's what limits do, is they assign a value to a value you can't get to. Okay, and there are finite limits and infinite limits. Okay, so a finite limit is represented by a real number. So in that example that we just had, where I'm squaring it and squaring it and squaring it every time, my finite value that I'm reaching is 0. 0 is the real number that it's being represented by. And that's because we have an end, and we call it measurable. And an infinite is never ending. It is not measurable. And it can't be represented by a real number. So if we take that 1/2, and instead of making it 1/2, we make it 2 and we square it, so we get 4, and then we square that, so we get 16, and we square that, so we get 256, so we square that, and we go forever and ever and ever. It's just going to keep growing and growing and growing, right? It'll never stop getting big. And that would be infinite, because it doesn't get close to any number. It just keeps getting bigger and bigger and bigger and bigger forever and ever. So that would be kind of the difference. This would be a finite because it's approaching a number that we can say, okay, this is getting really close to 0, so 0. But this one is infinite because it never gets close to any set number. It just gets big forever. Kind of makes sense? So with the continuous compounding, we'd be compounding infinitely many times per year. So if we were using the regular compound interest formula, n would be infinity. Question?
Yeah, she said that it's not there.
It's not here. It's on the printout. It's just, it disappeared, so I wrote it up here. I don't know where it went down here, but then I wrote over where it was, so I just moved it. But if you were looking, like I said, if you were looking at the old formula that we have for compound interest, it would be 1 plus r over infinity to the infinity times t. which is just infinity, because if you multiply infinity by any number, it's infinity, right? Okay, so this would be, but we can't do this formula. This is not solvable. So we use limits, okay? Now, if we look at the concept of the limit, we can make a table to see what happens as x approaches infinity. So we write that as x approaches infinity. So as x continues to get bigger and bigger, we see what happens to the function. So if I plug in 100, I'm going to do 100 squared plus 3 times 100 plus 5. And when I do that, I get 10,305. And if I plug in 1,000, I'm getting 1,000 squared plus 3 times 1,000 plus 5. And I get 1,000 or 1,003,005. And if I plug in 90,000, I get 8,100,270,005. And if I plug in 900,000, I get a number that is greater than 8 times 10 to the 11th, which is an 8 with 11 zeros. And if I plug in 8 million, I get a number that is greater than 6 times 10 to the 13th, which is a 6 followed by 13 zeros. And if I plug in 50 million, I get a number that is greater than 2 times 10 to the 15th. And do you guys see what's happening to this number? It's just getting bigger and bigger and bigger and bigger, right? So it continues to grow. Infinitely. When this happens, there is no limit. The limit is the number that it approaches. If it's not approaching a number, there is no limit, because there's nothing limiting it. Does that make sense? Function. Where'd my function go? Do you guys have your function? Is there a printed function on your paper right here? Okay. Yeah, no, it's on mine too, but it's not on here. So I don't know what happened to it, but anyway, okay. If I plug in 100, I get 6 times 100 minus 1 divided by 3 times 100 plus 2. And that gives me 1.983443709. And if I plug in 1,000, you know, it's 6 times 1,000 minus 1 over 3 times 1,000 plus 2. And I would get 1.998334444. And if I plug in 90,000, and 900,000, and 8 million, do you guys, notice anything? We're getting more and more and more nines, right? And what does that mean? What does this getting closer and closer and closer to? 2, right? We're getting closer to 2.
Will this ever get to 2?
No. We'll just get more and more and more nines in the list of this long decimal. Just more nines. We'll never hit 2. But as x increases towards infinity, f of x approaches 2. So we get closer and closer to 2. And so what we say is the limit of f of x as x approaches infinity is 2. The arrow here means approaches. And lim is for limit. And of course the sideways 8 is infinity. It's not actually a sideways 8, it's a Mobius strip, but that's beside the point. Okay, so you can have functions that approach a number. It will never get there, but essentially at this point it's basically 2. You've got a bazillion 9s after a 1. Essentially it's 2, but it's not 2. This one, we have the function 2 to the x, and we want to see if we can find a limit as x approaches infinity. So I'm going to make an x table and a f of x table, and I'm just going to pick 100 because that's a nice one to do, and then I get 2 to the 100. And then if I pick 1,000, what happens if I plug in 2 to the 1,000th? Oh, I get a number that's too big for the calculator. It errors out on me. So what do you think is happening as I increase x and I raise the exponent to this number? Is it getting close to anything? Or is it just going to go off in the distance forever, getting bigger and bigger and bigger and bigger? Yeah, it's just going to keep getting bigger. So it's going to increase in size forever. So there is no limit. We have some pretty set limits. The limit as 1 to the exponent of x as x goes towards infinity. Guys, if I take 1 and I raise it to the power of 2, 1 squared is 1. And 1 to the 3rd is 1 to the 4th, 1 to the 5th, 1 to the 10 millionth. Okay, guys, get a pattern? So we got that one. What happens if I put x on the bottom and I take it towards infinity? So I get 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. What am I getting closer to? Yeah, 1/100th, 1/1,000,000th, 1. I'm getting closer and closer and closer to 0. And then we have, oh, do me a favor. I did a typo on yours. There's a little x up here on yours. Cross that out. It should just be 1 to the 1 plus 1 over x. There shouldn't be the little exponent. So your exponent that's right here, cross it out. Doesn't exist. Okay. So what happens is the limit as 1 approaches infinity, or x, 1 to the x turns to 1, and 1 over x turns to 0. So this is 1 plus 0. So it's 1. But what happens when okay, yours is all nice and typed. Okay, so what happens is this is technically greater than 1 because it's not actually 0, right? It's 1.00000000000000000, whatever, right? It's really, really close to 1, but it's not really 1. So when we raise that to the power of x, we go back and forth. 70, 716, 718, 718, 718, 718. Like it's never going to get close to any whole number. Okay. But what it does do is it approaches a mathematical constant. It approaches E. And E is the base of the natural logarithms, and E is like pi. Except that it has a pattern. It's non-ending. It goes 718 and then 2818, 2818, 2818, 2818 forever and ever and ever and ever and ever. And E is what's known as the exponential base. So for, you know how we use 3.14 for pi, even though pi is much, much longer than 3.14 because it goes on forever? We use 2.718 or even just 2.7 for E, because E is 2.718, 2818, 2818, 2818, 2818 forever and ever and ever and ever and ever. So we just use this part of it. Okay, so what happens if you compound continuously? If we plug in the limit formula and we take the limit as x approaches infinity times our $1,000 and we plug it into this is our principal, 1 plus r, which is 100% over n to the nt, and n happens to be infinity, like I had shown you before, we would get 1,000 times that 2.718, 2818 forever, which would give us about $2,718.28. Okay. And this is if we were compounding continuously at 100%. But what if our rate isn't 100%, which it's not ever, because what bank gives you 100% interest, right? It's never going to happen. What if our rate is 4.3% or anything else? Well, then I'm going to have this limit as x approaches infinity of 1,000 times 1 plus 0.43 over x to the x. And I don't have the math to do this as x approaches infinity. Yeah.
So that kind of looks like our other thingy, the B.
It is. It's derived from that. Yeah.
How did the 210 have to be exempt for the 230?
Okay. So what we have is mathematicians, luckily, have derived the compound interest formula. For continuous compounding. Okay, so we have a compound interest formula for regular compounding. Is that B is equal to P times 1 plus R over N to the NT for continuous compounding. We have B is equal to PE to the RT, where E is 2.718. P is your principal, R is the rate, and T is the time. So you do the principal times 2.718 to the RT. My formula is B is equal to PERT. PERT. Okay, so remember E is 2.718.
Is E always that?
Yes, it's a mathematical constant. Sort of like pi is always 3.14, P is always 2.718.
Is that what that E button is on the calculator?
Yes. Huh?
E energy?
No, not in algebra or financial. No. E is energy in physics and maybe chemistry, but in math, E is a constant. It is the base of the natural logarithms. It is the exponential function. So 2.718. So we take our principal, which is 1,000. We're going to multiply that times 2.718 to our rate, which is 0.043, times the number of years, which is 5. So I'm going to do 0.043 times 5, which is 0.215. Whoops, I said 15 and I wrote 51. Then I'm going to take E, which is a button on the calculator. On this particular calculator, I have to do the second function E to the x. And then I put in my exponent, which is 0.215. And I'm going to get 1,000 times 1.239861897 and whatever. And I'm going to multiply it times 1,000.
So you just move the decimal place over 3, right?
Here?
No, in general, like answer because of the zeros. No, like,
Here?
yeah.
Oh yeah, 1, 2, 3. Yeah, basically, yeah. But if that wasn't 1,000, it would be, you'd multiply it times whatever. So this is first, to the power is second, and then the multiplication here is third. Okay, so you have to do rate times time first, and then you have to take e to that power next, and then you multiply it times your principal. Please. Simple interest gets us $43 in a year. So we'd have, our balance would be $10.43. Compounding monthly, so once a month gets us $10.43.86. We get that extra 86 cents. Compounding daily gets us an extra 94 cents. Compounding continuously gets us an extra $200. Oh yeah, you're right. Okay, times 5. I forgot to do the times 5.
Okay. That's what I was missing this whole time.
That's right. Yeah, I messed up on that too. 1,000 times 0.0 times 5. Oh, 215. That's different. 0.043 times, nope, not times, divided by 12 plus 1 raised to the power of 60 times 1,000. Okay, so yeah, it's really not that big of a difference. So it really doesn't get you a whole lot more money compounding continuously. But it does get you more.
I'm reading the homework and stuff. How do you find it every hour?
I want to calculate the future value of a single deposit. So I take some money today and I put it in the bank, and it's my single deposit. I never touch it. I never put any more money in. I never take any money out, and the interest rate never changes. You use the compound interest formula. But most people don't do banking that way. That's not how you save money, right? You don't just stick some chunk of money in the bank today and then that's it. You don't do anything. Most people make periodic investments or periodic deposits, and that's where you put the same amount. So regular basis. So let's say you get paid every 2 weeks and you put $50 every 2 weeks in a savings account. Then we can calculate the future value. So how long will it take us, or how much money will we have rather at the end of a certain amount of time. So how much money will you have in 10 years if you put away $50 every 2 weeks? Yeah. So let's say $100 a month, $50 every 2 weeks, or whatever. Okay. So this is the formula to calculate that. So for periodic investments or periodic deposits.
Seems a lot more complicated than it has to be.
Nope, it's not. It's exactly the way it needs to be. It's very elegant. Okay, so in this instance, B is our balance. At the end of whatever time period we choose. P is the periodic investment. Okay, so P is that $100 we put in every month, or that $50 we put in every 2 weeks, or $25 a month, or whatever. R is the annual interest rate. N is the number of times it's compounded annually. And then T is the number of years. Okay. Now here's where this one gets a little bit. The periodic investment amount you want that to match the N. So if I'm compounding monthly, then I want to make my periodic deposit monthly. Even if I'm putting in money every 2 weeks, so let's say I put in $25 every 2 weeks, I'll say $50 because that's $50 a month.
P is not the same, because the P was principal.
Yeah, it's principal. This time it's the periodic investment. P always is the money in the account or the money you're putting into the account.
So P and N have to be the same?
Not the same number, the same. So like let's say hypothetically you get paid every 2 weeks. And you're going to put away $50 every 2 weeks out of your paycheck into savings. But if your bank account compounds monthly, you're not going to say P is $50 because that's every 2 weeks. You're going to say P is $100 a month. Does that make sense? So you want it to the time period to match. So if I'm putting in $100 a month, but it compounds daily, I'm going to divide that 100 by the number of days and say I'm putting that much in daily.
This is the next example, and I think we'll get it.
Yeah. I just wanted to.
You just wait 1 second.
Rich and Laura are 45 years old, and they open an account, and they're going to hope to gain enough money to retire at age 65. And they're going to deposit $5,000 a year into that account. Interest is 4.5%, and they're compounding annually. Okay, so N is going to be 1 because we're compounding annually. R is going to be 0.045. T. They're 45 and they need it to run until they're 65. So T is how many years? 20 years. Okay. And then P is $5,000 because that's how much they're going to put in every year. And we've already got this one set up to where we're talking about an annual deposit, annual compounding. So those match. 1 year, 1 year. Okay. So my equation divided by R over N. So 5,000 times 1 plus 0.045 divided by 1 to the 1 times 20 and 0.045 divided by 1. So 5,000, this is 1.045 to the 20th. And I got that because 0.045 divided by 1 is just 0.045, then plus 1, which is 1 point. And then that's 0.045. And 1.045 to the 20th is 2.411714025 minus 1.
You times it by 5,000 already?
No, sorry. I'm doing it in the calculator in one steps, and I'm not writing everything down here. Okay, so at the end of 20 years, they're going to have $156,000, well, $156,857.11. Okay. They're putting in $5,000 per year, which is $100,000. That's how much they've deposited. And so the interest they earn is $56,000